trigonometric functions are the cosine, the sine, the tangent, the cotangent, and then, well, a couple more that I'm going to introduce. Okay. Well, these functions are defined in a geometric sense. Okay. So if we draw the unit circles, okay, so this is the unit circle. So that's the circle that starts at the origin and has a radius, is central at the origin, and has a radius 1. Okay. If you take an angle of this circle, and we call it x, and we're going to talk in radians here, so one turn around the circle is 2 pi radians. Okay, so become familiar with radians, please, because we're going to deal with them a lot. Okay, so x in radians, an angle x, the definition is that the sine of x is this vertical line in the triangle that you obtain when you go from here to here. Okay, and the cosine is this horizontal line. Okay, and now using geometric arguments, you can see that the tangent, which is the sine of x divided by the cosine of x, is just this length. Okay, because, well, using this similar triangle argument and uses Thales theorem, you have if this is, let's see, we have two triangles, right? And they are similar because they are both right and they have the same angles here and the same angles here. Okay, so this is x and this is y and this is 1. Then this length is proportional, so the ratio between the lengths are proportional, right? So x over y is the same as, let's call this t over 1, right? So in this case we have t is the tangent, and then x is the sine, y is the cosine, right? So that's how you define the tangent. And the cotangent is the inverse of the tangent, so this is the cosine of x divided by the sine of x. Okay, so I'm using similar geometric arguments. You can see why this is the length of the cotangent. Now there are two additional trigonometric functions that we will see during the course. First is the secant of x, which is 1 over the cosine, so secant, and the cosecant of x, which is 1 over the sine of x. Okay, cosecant. So they're useful in that it's easier sometimes to write things instead of 1 over cosine. We just write a secant again, and they'll appear prominently when we deal with integrals later in the course. Okay. Okay, so that's the kind of geometric definitions. When we plot these functions, we have the sine of x is this function that I told you before. So this starts at 0. The sine of 0 is 0. It goes to 1 at pi halves. So this is pi halves. It goes to 0 at pi. This is pi. Then it goes to -1 at 3 pi over 2, and then it goes back to 0 at 2 pi. And this is the basic form of the function that it gets repeated throughout. Okay, this is the periodic function. So when you have the same form here, the same form here, right? And as we have said before, the sine is an odd function. Okay, so sine of -x is equal to the sine of -x is minus the sine of x. Okay, so as you can see, the copy of the function in the negative part of the x-axis is just the same as the positive one, but just mirror down against the x-axis. Okay, and the cosine, as you can see, is the same as the sine but shifted. Okay, as you can see, it's the same function. It goes down and up, right? It's the same form. It's just the shifted pi halves over to the left. Okay, so the cosine at 0 is 1, then it becomes 0 at pi over 2, it becomes -1 at pi, and it becomes 0 again at 3 pi over 2, and then 1 at pi, right? The difference between the sine and the cosine is that now the cosine is an even function. The cosine of minus x is equal to the cosine of x. Okay, so if you see the function, the blue line here, the copy of the function is just the same as the positive part, but mirrored down left with respect to the y-axis, right? And now, so the tangent is interesting because it's the fraction between the sine and the cosine. So it's going to be 1 when the sine and the cosine are the same, and this happens when x is pi over 4, because this is what you would call 90 degrees, but please get used to this. Pi over 4 is 90 degrees, it's a right angle, okay? So this is the point where a tangent gets to 1. Now when the sine of 0, so when the sine of x is 0, the tangent is 0, so that happens at 0 and then at 2 pi and, you know, every other, what is this, 2 pi? No, this is pi, sorry. So it's at 0, at pi, at 2 pi, and so on. And interestingly, at pi over 2 and minus pi over 2, and these values where the cosine goes to 0, as we have seen, the tangent goes to infinity, because this, as the cosine gets smaller and smaller and smaller, the fraction gets bigger and bigger and bigger. So this gets growing until it goes to a point in which the denominator is 0, so that the function doesn't make sense. So here at pi over 2 we have what we call a vertical asymptote. Okay, so it's a point that's not in the domain of the function. Okay, so the domain of the tangent is not the reals. Okay, so the domain of the sine is the real line, the domain of the cosine is the real line. The domain of the tangent is not the reals, it's the reals except those points where the cosine is 0, right? So it has this form, and again it's periodic because it's the division of two periodic functions, so you have a periodic copy. Okay, so this form gets copied in windows of width, again 2 pi, width pi. Okay, so the period of the tangent is pi, and the cotangent is kind of the same, but instead of going upwards it goes downwards, and the lines where its vertical asymptotes are not minus pi over 2 and pi over 2, but rather at 0, which is where the sine is 0, and then at pi, and then 2 pi, and so on. Okay, so you have this vertical asymptotes for the cotangent, and the cotangent does this